Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss problems on quantization. Okay. So quantization, the meaning of quantization we must know. Why? We are going to convert any analog signal into digital one. Quantization is must. Quantization means we are going to discrete the signal in amplitude. Why? Because before quantization we are going to do sampling. Sampling means we are going to discrete the time domain. But amplitude is continuous. After sampling, you get the output as a discrete time continuous amplitude. So when you convert any analog signal into analog to digital one, we must get the pure discrete form. That means both the time and amplitude is going to discrete. So the quantization is a process to convert the continuous amplitude into discrete amplitude. Okay. So that is the meaning of quantization. So we are going to do some problems on quantization. Quantization levels or quantization error, whatever it may be. Okay. So entering into the course outcome. So this course outcome covers module 3 and it states illustrate the concept of pulse modulation schemes, demodulation, sampling, quantization and coding for obtaining a digital data. So here we are converting analog into digital one by performing all the functions, that is sampling, quantization, then coding. Then we're going to get the digital signal. Okay. So coming to the problem. So the first one is given audio signal bandwidth having a W is equal to 15 kHz. The number of uniform quantization levels is 512. Find the Nyquist rate and the minimum sampling rate. So here it shows audio signal. Audio signal means it is a continuous one. So we are going to digitize this analog signal. So we must require this Nyquist rate and the sampling rate. Okay. So by using this given data, we are going to solve this problem. So here the bandwidth is given as W. Okay. So first you go to write the given data. Given this W is equal to 15 kilohertz. Okay. And quantization levels L is equal to 512. Okay. L equal to 512. So this is the given data. By using this given data, we are going to find the Nyquist rate. So Nyquist rate is nothing but 2W. Okay. So the first problem is Nyquist rate. It is equal to 2W, that is equal to 30 kilohertz. 30 kilohertz. And second one, the given levels, quantization levels. Why? Because here we are going to convert the continuous amplitude into discrete one. Continuous amplitude into discrete one. So here having different levels are, that is the discrete levels. The discrete levels can be also called as represent levels. So these levels having some voltage. That means we are going to round off, near of value we are going to round off to that discrete level. Okay. So here L is 512. So we know that L equal to 2 power n. N is the number of bits required to represent the signal. Okay. So here my L is 512 and you're going to find 2 power n. Okay. So 2 power n is equal to 512. It is equal to 2 power 9. 2 power 9. 512. So here my n is equal to 9. So the sampling rate or the Nyquist rate. So here first we go to find the Nyquist rate now. So the Nyquist rate is 30 kilohertz and the Nyquist interval is nothing but 1 by Nyquist rate. So 1 by 30 kilo. So it gives 1 by 30 milliseconds. Okay. So the Nyquist interval is equal to 1 by 2W. It is equal to 1 by 30 kilo. So this kilo goes to the numerator. You can take it as a millisecond. So this is the Nyquist interval. From the Nyquist rate, you are going to find the Nyquist interval. So this 1 by 30 milliseconds must be divided to the 9 bits. So why? Because here you got the bits is 9. So this 1 by 30 must be divided to the 9 bits. Okay. So the minimum sampling rate for this signal is 30 into 9. Why? My Nyquist rate is 30 kilo. How many bits? 9 bits. So 30 into 9 gives 270. Okay, 270 kbps, kilobits per second. So this is the minimum sampling rate required for the audio signal. Okay, so 270 kbps, and you can convert this kbps into megabits also. So 0.27 mbps. Okay, so this is the problem. Coming to the second one. So the second one also signal, but here this is video signal, whereas the previous one is audio. But in this problem, video signal is given. Given video bandwidth is 4.5 megahertz. Sampling rate is 15% in excess of the Nyquist rate. Uniform quantization levels are 1024. Find the permissible bitrate. So we're going to find the bitrate here. So what they given? The bandwidth is given. The sampling rate is given. But the sampling rate is excess of Nyquist rate. So first you go to find the Nyquist rate and excess of 15%. And they given another data is levels, quantization levels or repression levels. So L is given, W is given. Okay. So first you go to find the Nyquist rate. Okay. So first Nyquist rate. So the Nyquist rate is equal to 2W. So the bandwidth is 4.5. So 2 into 4.5 megahertz. So this is 9 megahertz. And already you know that. Why? Because the audio signal requires a very less bandwidth than compared with the video. In the previous problem, audio bandwidth is taken as in kilohertz, but in the video, it is in megahertz. Okay. So the actual sampling rate is 15% excess. Okay. So actual sampling rate is 15% excess in Nyquist rate. So sampling rate. The sampling rate is 15% excess of this one. So 15%. So 15 by 100. Okay, 15 by 100 into this 9 mega. Okay, so it is 0.15 into 9 megahertz. So approximately it may be 10.35 megahertz. You can use calcium mustard for finding the values. Okay, so the sampling rate we got Then we go for the sampling period. So the sampling period here, Ts is equal to 1 by Fs. Simply you can take it. So what you got? 10.35 megahertz. So we go to substitute this 10.35 megahertz. So when you move this megahertz into the numerator, it is going to microseconds. Okay. So simply it is 1 by 10.35 microsecond. Okay. So here in this problem they give another data L. Okay. So here this sampling rate must be divided that number of bits. Okay. So here L is 1024 and we know that it is 2 power n. So here you can write this it is equal to 2 power 10. So my n is equal to 10 for this 1024 levels. Okay. So the bit duration here is Ts by 10. So already we got the Ts. Ts value is sampling period, sampling duration is equal to 1 by 10.35 microsecond. So again we are going to divide this. Okay. So it gives 1 by 103.5 microsecond. So what is the permissible bit rate? Simply inverse. Okay. Simply inverse. So you get in terms of megabits per second. Why? Here it is in microseconds. So when you go to inverse, so you get in Mbps. So here it gets 10 power Mbps. So simply you can write your 103.5 Mbps. So this is a permissible bit rate, or B is equal to this one. Okay. So this is a problem. Now we go for another problem. So here this is a problem regarding on delta modulation. But actually here it is also linked with the quantization. So without quantization we can't use any digital system like PCM or DM, whatever memory, DPCM, ADM, any system. So sampling, quantizing is must assured. Okay. So this problem. Consider a delta model system used to transmit a voice signal which is uniformly sampled at a rate of 64 kHz. Assuming the following specifications, voice signal bandwidth is 3.1 kHz, maximum signal amplitude 10 volts. So here they ask to avoid a slow power distortion, what is the minimum permissible value of the step size delta used in the system? Why delta? That is a 2mx by L step size. Determine the average power of granular noise. And third way, determine the minimum channel bandwidth needed to transmit the DM encoded data. So it is a digital signal. So for the digital signal we are using system DM, delta model system we are using to convert this Y signal into digital one. So the final output is the DM encoded data. Okay. So these are the given. Okay. So let's solute. So sampling rate is, so first you go to write sampling rate is 64 kilohertz. That is given 64 kilohertz. And another one is voice bandwidth. So voice signal bandwidth. So voice signal bandwidth is equal to 3.1 kilohertz they given. And maximum signal amplitude. So here the signal amplitude is 10 volts. Okay. So maximum signal amplitude. Sorry, this one is maximum signal amplitude, that is equal to 10 volts. Okay, so this is one. So what the first one asked, the first problem, to avoid the slope overload. Why? Because here two types of noises are coming in delta modulation. One is the slope overload, another is the granular noise. Okay, so here in any system, digital system, our aim is the analog signal must be catched by the representation levels. Why? We are giving this analog signal to the quantizer. The quantizer contains representation levels. So these levels is going to convert this analog amplitude, discrete amplitude by the near round off. Okay, so the signal must be within the representation levels. Okay, so in case it exceeds, it is got the slope overload. The levels is above this signal, then we got the granular noise. Okay, so first one, to avoid the slope overload, here you having a maximum amplitude must be less than by delta by 2 pi fm ts. 2 pi fm ts. Okay, so we know that delta step size. Okay, and we know that A max, that is maximum amplitude, FM signal frequency, TS sampling duration, sampling time. So here what they ask, you find the delta step size. In this problem, you're going to find the step size, how much to avoid the slope overload. Okay, so here rearranging this formula, then delta is equal to Fs divided by 2 pi Fm A max, this one. So why? Because 1 by Ts is nothing but Fs. Okay, so here we know that Fs, okay, we know that Fm, we know that A max. We go to substitute all these values. So Fs is 64 kilohertz divided by 2 pi Fm. Our signal bandwidth 3.1. So 3.1 kilo into maximum amplitude, the given 10. So here this one also kilohertz. So numerator both having the same kilo, you go to cancel, and by using calci you get the step size value delta is equal to 0.33 volts. So this is the answer for this problem. So this is the step size, required step size to avoid the slope overload. Why? Because here this is like the signal, here this one, this is analog signal, here this is the step size provided. So the step size is going to catch this analog signal. So if it fails, then you got this noise. This is slope overload. So we are going to avoid this slope overload. So we are going to maintain this step size. So here the step size is fixed. This one is the delta. So my delta's value is 0.33 volts to avoid the slope overload. So after avoiding the slope overload, this is go like this. This one. So when you arrange the step size, value is 0.33 volts, then you can get the digital signal without any noise. And coming to the B bit, so in this problem B bit also there. So what the B bit? Find the granular noise power, granular noise. Already we mentioned in the last bit, two types of noises are arising. One is slope overload, and then is the granular noise. Okay. So for this granular noise, we know that 2 by delta, minus delta by 2 to delta by 2 q square dq. Q square dq. So the q is a quantization noise. Okay. So for solving this one, integrating 2 by delta into q cubed by 3, and the limits are minus delta by 2 to plus delta by 2. Okay. So after substituting these values, so finally we got to delta square by 3. Delta square by 3. So in the previous one, what you set the delta value? The delta value is set as 0.33 volts in the first bit, a bit or 1. Okay. So delta is 0.33 volts. So the average power. Okay. So here you go to substitute this value, then the average power. Here we know that if any power required, the resistance value. Okay. So here the resistor or the load which we assumed as 1 ohm, simply 1 ohm. Then the average power of the granular noise is 0.03 volts. So you go to substitute 0.33 square. Okay, divided by 3. And it is passing through a 1 ohm resistor. Then the average is 0.03 volts. Okay, so 0.03 watts. Coming to the C bit. Coming to C bit. So what is the minimum channel bandwidth is needed to transmit DM encoded signal? Okay, so it is just inverse of the sampling rate. Inverse of the sampling rate. So what is the inverse of sampling rate? That is nothing but 64 kilohertz they given sampling rate. Okay, so there is a minimum bandwidth required. Okay, so that is a third problem. Okay, so here we go. So another one is a delta modulator system is designed to operate at 5 times the Nyquist rate for a signal having a bandwidth equal to 3 kHz bandwidth. Calculate the maximum amplitude of a 2 kHz input sinusoid for which the delta modulator does not have slope overload, given that the quantization step size is 250 millivolts. Yeah, they given delta here 250. They given FM. Okay, so here we're going to calculate the maximum of 2 kHz input sinusoid does not having the slope overload. So for this problem, we must take in the slope overload condition to avoid the slope overload. What is the condition required? Okay, so that is already done in the previous one. Okay, so before going to this solution, so we are going to write the given data. Okay, so here FM is 3 kHz. Nyquist rate from this FM, the Nyquist rate is equal to 2 FM. So 2 into 3 kilo. So it gives 6 kilohertz. Okay, and the sampling frequency. Sampling frequency. So in this problem, they mentioned the sampling frequency is must be 5 times. Okay, so 5 into 6 kilo, then it gives 30 kilohertz. This one is an Nyquist rate. This is a sampling frequency. Now sampling interval. sampling interval. So that is nothing but 1 by sampling frequency. So 1 by 30. So 1 by 30 kilo. So the kilo enters into the numerator, it is in milliseconds. Okay. So it is 1 by 30 milliseconds. Here we could write. And they given the step size. So what is step size? 250 millivolts. So there is a step size. The step size means it is the space between the two representative levels. Spacing between the two representative levels. That means here we are going to digitize some signal. So like this. So this one. So these are the representative levels. And the spacing between these two levels is called step size. If they are uniform, you can call it as a uniform quantizer. If they are not uniform, you can call it as non-uniform quantizer. Okay. So the given delta value is here 250 millivolts. Okay. So 250 into 10 power minus 3 gives 0.25 volts. Okay. This one. And what is the FM? FM is 2 kilohertz. Why? Because they have given condition for 2 kilohertz signal, we are going to get the slope overload. Okay. So to avoid slope overload, we must know the formula. That is AM is then equal to delta 2 pi FM TS. Okay. So here AM is then equal to, so what is delta? 0.25 volts divided by 2 pi FM. So 2 pi FM is 2 kilo and TS sampling intensity is 1 by 30. 1 by 30 K. So here also K. So this K is going to cancel, and by using calc, we are getting this value as 0.6 volts. So this is the maximum amplitude. The maximum amplitude of signal must be less than equal to 0.6 volts. Okay. So coming to the problem, fifth one. So in this problem, determine the output signal to noise ratio of a linear delta modulation system for a 2 kHz sinusoidal input signal sampled at 64 kHz. Slope overload distortion is not present, and the post reconstruction filter has a bandwidth of 4 kHz. Okay. Okay. So here it is in the form, that is this problem is related with the delta modulation system. Okay. So here signal to noise ratio we are considering. Here we determine the output signal to noise ratio. So we must require the formula. SNR output is equal to 3 FSQ divided by 8 pi square FM square FM. Okay. So here the given data. So here the given FS, the given FM signal bandwidth, and FM is the reconstruction filter bandwidth. One is the signal bandwidth, the other is the reconstruction filter. Okay. So this is SNR output, signal to noise ratio. Okay. So that means it is at the receiver. So the earlier problems are discussed at the transmitter side. Now this problem is related to the receiver. Okay. That means we are sending the signal and it propagates in the channel, and finally we are received at the receiver. So the receiver is going to receive signal, and we are going to calculate what is the SNR, how much signal to noise ratio. If the signal is high or noise is high. If noise is high, the signal quality is very less. So we must require the signal than the noise. Okay. So this is a formula. So for this formula, we are going to substitute all the values and get the answer. Okay. Okay. So first given Fs is equal to 64 kilohertz, Fm is 2 kilohertz, and capital Fm is 4 kilohertz. So one is the frequency, sample frequency, another is the signal, and another is the filter. Okay. So SNR output is equal to 3 into Fs cube. So what is Fs? 64 kilohertz. So 64 into 10 cube means kilo. So this is Fs. Fs cube divided by, and here 8 pi square. So this is constant left. 8 pi square into Fm square. So Fm square means a signal kilohertz. So here 2 into 10 cube Fs square into Fm. Fm is 4 kilo. So 4 into 10 cube. So this is the formula. Just we are going to substitute all the values in this formula. Okay. So by using calci, simply we can solve this problem simply. Okay. So by using calci, you can get 62.51. So this is my SNR. But it must be in dBs. So apply 10 log base 10 of the 62.51. Then we got 27.94 dB. So this is the my final signal to noise ratio output. Okay. This is the way to solve this problem. Now coming to the sixth one. So calculate the signal to quantization noise ratio of a PCM system which has the same data rate of 64 kbps. The sampling frequency is 8 kHz and the number of bits per sample is 8. N is 8. So here you go to find the SNR output for a PCM system. Whereas in the previous one, that is a DM, delta model system. But in this problem, they asked the signal to quantization ratio for the PCM system. Okay, so the PCM. So it is very simple formula and dB directly. So this is a direct. Before this getting this formula, there is a derivation is there. After solving all this derivation, simply this is the data. So here we must require number of bits. That's all. So the number of bits is given at 8. So just you go to substitute this value and the final output is in dB. So this is the formula for PCM system, signal to quantization noise ratio. Okay. So 1.8 plus 6 and so 6 into 8, 48 dB. So 48.1, 49.8 dB. So this is my signal to quantization noise ratio for a PCM system. Okay. Now is another problem. Yeah, this one. So a sinusoidal Y signal x of t is equal to cos 6000 pi t is to be transmitted using either PCM or DM. The sampling rate for PCM is 8 kHz and for the transmission with DM the step size is decided to be 31.25 millivolts. Assume that the number of quantization levels for a PCM system is 64. Okay, so they given L value, they given delta value, they given sampling fs and they given fm also. Y x of t is equal to cos 6000 it. Okay, so by using this given data, we go to solve this problem. So first the signaling rate. The signaling rate for the PCM. Okay, signaling rate. So here you go to write signaling rate for PCM. For PCM is equal to R is equal to N Fs. R equal to N Fs. So we go to know the N value and Fs the given. So how to get the N value? So there is L equal to 2 power N. What is my L? 64 is equal to 2 power N. So here you get my N in terms or N equal to log 2L, whatever it may be. So finally here it is equal to 2 power 6. So that is 2 into 2 into 2 into 2 into 2. 2 2s are 4, 4 2s are 8, 8 to the 16, 16 to the 32, that is 64. So N value is 6. Okay. So we go to substitute the N value in this problem. Okay. So R equal to N 6 into Fs. So what is Fs here? This problem 8K. So 8K, that is 6 8s are 48 kilohertz. So this is the sampling rate. So signaling rate. This is the signaling rate for a PCM is 48 kilohertz. But here it is going to avoid the slope overload. Then simply again you take the delta by 2 pi fm dx. So this is the formula for delta modulation. Okay. So here it goes to numerator. So but they ask the signaling rate for the delta. So it gets from the Fs. So again modify delta Fs by 2 pi Fm. So I required Fs is greater than or equal to is 2 pi Fm A by delta. A by delta. So this is my Fs. So they given Fm, they given amplitude, and they given delta. Okay. So here you go to substitute this value. 2 pi is constant. Fm 3 kilo and A is 1. Delta 31.25 into 10 power minus 3. So all is given in data. Okay. So now we go to use the calcium. Then the Fs is greater than or equal to 603.18 kilohertz. Okay. 603.1 kilohertz. What is one? Signaling rate for delta modulation. This is for delta modulation without slope overload. Okay. So this is the problem. Coming to the 8th problem. A 10 kilohertz sinusoid with amplitude levels of plus or minus 1 is to be sampled and quantized by round off. How many bits are required to ensure a quantization SNR of 45 dB? What is the bit rate of digital signal if the sampling is chosen as twice the Nyquist rate? So the given sampling rate is twice of the Nyquist rate. Twice of the Nyquist rate. Okay. So here sinusoid signal. So here taken as F0 is 10 kilohertz and amplitude levels amplitude levels plus or minus 1 volt and SNR is required 45. Okay, so here P equal to 1 by root 2 whole square, so 1 volt amplitude, so 0.5 watt. So this is my power. Okay, and noise power, signal power, this is signal power, and noise power is delta square by 12. Okay, delta square by 12. So what is delta? Delta equal to 2m max by L, 2m max by L, or you can return L equal to power n also, put it maybe. But what is m maximum? 1. So 2 by L, simply delta. So here you go to substitute the SNR output is equal to signal to quantization ratio. So signal is 0.5 or P, what it may be. So 10 log P by sigma square cube, sigma square cube, this one is sigma square cube, this one, signal to quantization noise ratio, SNR here. So substituting all this value, then you got 10 log delta square by 6, this one is. So coming to the next slide. So here you go to substitute 10 log of 2 power to n, L value 1.5, this one. So then you got 45 dB by using. Okay. So since 6 dB corresponds to the SNR output for 1 bit, so we get n equal to 8 bits. So Fs equal to 2 FM. It is 20 kilohertz. The given FM is 10 kilo. Okay, so FM is 20. And the bit rate NFS. So 8 into 20 K. So it is 160 K kilohertz. Okay. So this is the solution for this given problem. And ninth one. The signal G of t is equal to 2 cos 2000 pi t minus 4 sin 4000 pi t is quantized by rounding off using a 12-bit quantizer. What is the RMS quantization error and the quantization SNR? Okay. So first taking the given signal, that is G of t is equal to 2 cos 2000 pi t minus 4 sin 4000 pi t. Okay. And the number of bit is 12. This is the given number of bits is 12. And the signal power. So we're going to find the signal power is equal to 0.5 into 2 square plus 4 square. So simply it is 10 watt. So here assumes that resistor is 1 watt. Okay. So the peak value. So delta is equal to 2 mx by L, 2 mx. So here 2.6 by L, that is 12 divided by 2 power n. So approximately substitute n value is 0.029. Okay. And you got to find this sigma q. It is a delta by square root 12. So 8.457 into 10 power minus 4. And final the signal to quantization ratio output, that is 10 log P by this sigma square Q. So you are going to substitute this 10 log of P value is 10 divided by this 8.457 into 10 power minus 4 whole square, and finally you are getting 71.46 dB. So that means for solving these problems we must require the calcium. Without calcium you can't do this digital communication or ADC problems. Okay. So coming to the 10th problem, very big problem. So the data from 10 different sources are brought to a processing center over wide sample, quantized, binary coded, and TDM, time division multiplex. The multiplex data are then transmitted to the model system. The bandwidth of each signal is 100 Hz. The maximum acceptable error in the sample and amplitudes is 0.25% of the peak signal amplitude. The sampling rate must be at least twice the Nyquist rate. Determine the minimum cable bandwidth needed to transmit this data. Okay, so this problem already all explains how the signal is going to process and transmit it. Okay, why? Because this problem explains step by step how many sources are coming to the center via wires, and next process is sampled, quantized, binary encoded, and all these 10 sources are going to multiplex. This multiplex signal is again transmitted to the model system. Okay, so this is explains how this signal is going to process this problem. Okay, so now the Nyquist rate. The first one is Nyquist rate. So it is nothing but 2 FM 200 Hz, and the sampling rate. So the sampling rate is twice of this Nyquist rate. So twice means 2 into 200 is 400 Hz. Okay. So total number of samples for 10 signals. So total number of samples for 10 signals is equal to 10 into 400 is 4000 Hz. Oh, this is samples, so not mentioned as Hz. 4000 samples per second. Here simply 4000 samples per second. So quantization error. So you must come this error. Why? If you are going to quantize, some quantization error is must arise in any system. Okay. So that is given as 0.25 maximum flexibility given. Why? Because you got this problem. So 0.25% of the peak signal amplitude. This is the acceptable error, minimum acceptable error. So that is 0.25 max. Maximum amplitude divided by 100. So here this is M max. So M max, maximum amplitude. So that is equal to M max divided by 400. Another one is the peak quantization. Peak quantization error. Delta by 2. So again you got delta is equal to max by L. So here it is M max by L. So now we are going to equating these two. One is M max by 400 and another is M max by L. So simply my L is 400. So it is in the power 2 power of, you can write. So nearly it is 9 2 power. Okay. So n is 9. So n is 9. Okay. So after getting this n value, we are getting the minimum bit rate. Minimum bit rate. So minimum bit rate. So that is n into fs. So 9 into fs. So what is my fs? 4000. So that is 36,000 kbps, or simply 36 kbps. 37,000 bits per second, or 36 kbps. This is the minimum bit rate. And minimum bandwidth. So for the minimum bandwidth for the cable, they ask minimum bandwidth. That is half of this 36 kbps. That is 18 kbps. Okay. So this one. So this is the solution for this one, and this one is the last one. For a binary PCM signal, determine L if the compression parameter mu is 100 and the minimum SNR is 45. Determine the SNR with this value of L. Okay. So here the minimum SNR is 45 dB. So 10 log SNR is equal to 45. Okay. So we go to substitute this SNR. So SNR output is equal to 62.7. Okay. So this is my SNR. So substituting all these values, so then you get this required SNR. Okay. So the minimum SNR we are getting. So this is the references. The content of information is taken from the Saman Hacking, commission of Saman Hacking, and also commissioned by Chakrabarti. Okay. Once again, before going to this, this will go to solve. So SNR output is equal to 3L square by ln of 1 plus mu whole square. So here you go to find. So forget for finding this L value. So this is the formula for L value. So substituting these values. So SNR we got 3162.77, that is equal to 3L square by compression value 1 plus mu, that is 100 mu is given. So ln value is 101 mu whole square. Okay. So substituting this value, then you get this L value is 473.83. So approximately we are going to L value is approximate 512 nearby. Why? Because here it is taking the 2 powers. Okay. So this is, we select L value is 512. Then you are getting SNR output for this L value. So 3 into 512 whole square divided by same formula ln 1 plus mu, that is 100 101 whole square, ln value 101 whole square. Then you are getting 36,922.84. So if you require dBs, so SNR in dBs just you could apply 10 log of this one. 10 log is 10 of 36,922.84. Then you got 45.67 dBs. So this is the problem for this. So in this problem, they ask two values. One is you go to find the SNR, and again you go to value of L. So by using L, you getting final SNR. Okay. So by using given data, mu value, SNR value, you are find the L, and again by using this L, you are get this SNR. Okay. So that's why here first you go to find the L values, represent levels. For these levels, the SNR output is 45.67 dBs. Okay. Okay. Thank you, students. So now references are taken from Summer Hacking, Community Systems, Method Edition, and Chakravarti and Haribhat also we considered for these problems. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.